Okay, welcome back everyone. We talked last time about two things which will be quite important for the following. The first thing was this Minkowski metric, eta mu nu, which will accompany us for a while. And the other thing was Lorentz transformations. I should put again the relevant things on Lorentz transformations on the board. Or, so recall. Lorentz transformation is a linear transformation which gives me new coordinates x mu tilde in terms of old coordinates x nu just by multiplying it with the coefficient matrix. And I write it in this form. So last time one of you asked me where this index rho belongs to, if it belongs to the x or to the L. Of course it belongs to the L. Yeah? So L has two indices. And there's a particular reason why I don't write them one above the other, why I really leave a little space here. I think that's quite important to leave this. I'll say something about this in a minute. And the property which defines the Lorentz transformation is that this thing leaves this Minkowski metric invariant. So if I do something like that, if I multiply both entries of this eta with the Lorentz matrix, so then I get something of this form, then I should get back the Minkowski metric. So why do I not like to write these two things one over the other? The reason is that later we will raise and lower indices. So for instance, we might introduce something like that. When we have this thing here, L mu nu, we might like to raise one of these indices. For instance, we may like to lower this index mu. We would do this by multiplying this with this eta. So this was this rule which I briefly mentioned already and which we will use later in the course quite frequently, that you raise and lower indices with the help of this eta. So that would be denoted L rho nu. You see the mu is summed away. So the whole thing depends only on the indices rho and nu. So that would be the standard notation for this. And now you observe that this is not the same as the thing with the indices interchanged. So if you write the two indices one above the other, then you don't know which index you pull in a particular place, right? So if you write one over the other, then let me make this as a remark here. If I do something like that, L mu nu eta, what had I here? Rho mu. So is this the same as pulling the mu here to this place or pulling to this place? Yeah, I cannot read it from this expression. So is this the same as L mu nu, or is this the same as L nu, nu rho or rho nu? And that's not the same thing. So that's the reason why you shouldn't write the indices one above the other. Actually, there's a second reason. If you translate this in the matrix equation, you can read this as a column vector, and this as a column vector, and this as a square matrix applied to this column vector. Then you would need to know which one is a column index and which one is a row index. The traditional convention is that the first index labels the rows, the second index labels the columns. But if you put them one above the other, you don't know which one is the first, which one is the second, right? So you wouldn't know how to translate this into matrix notation. That's the second reason. So I deliberately left a space here. Okay? Yeah? Question?
Yeah. Shouldn't the row be a nu in order to get some convention?
Very good remark. Yes, thank you. Some index was wrong. Yeah. So I could also the other possibility would be to make both into a nu, but they should be the same thing. Thank you. Everything else correct? Yeah, you will realize that I always make mistakes of this sort, that I get in the indices wrong. This is it's a good exercise for you to find the errors in my lecture notes. Good. So much for the for repetition from last time. And now we want to talk a little bit more about Lorentz transformations. Actually, I want to discuss briefly two particular types of Lorentz transformations. The first one will be spatial rotations, and the second one will be the famous boosts. And this will give us the opportunity to practice a little bit this juggling with indices. Two types of Lorentz transformations. So the first one is spatial rotations. That's the thing one of you already mentioned last time. This should be a transformation which transforms inertial systems into inertial systems. And for simplicity, I will write them down explicitly only for the case that it's rotation about the x1 axis. So how would this look like? So I write a rotation about the x1 axis in this form. So I get new coordinates, x0 tilde, x1 tilde, x2 tilde, x3 tilde, by applying a certain matrix to my original column vector x0, x1, x2, x3. And how do I have to do this if this is supposed to be a rotation? Well, it's a rotation about the x1 axis. So only x2 and x3 are affected. Yeah? The axis remains unchanged. So I have ones here and zeros here. And nothing happens in the mixed terms. And this interesting thing is here. So I want to have a rotation of this axis about a certain angle phi. So I would have here cosine phi, sine phi, minus sine phi, cosine phi. So this is obviously parameterized by an angle which I called phi. Okay, and I think everyone is able to translate this into a picture. So the relevant thing happens in the x2, x3 plane. So that's what I draw here. So that's a purely spatial picture. Time is not shown in this picture. And then I have my rotated axis, and they are rotated by a certain angle phi. So I have x3 tilde here, x2 tilde here, and that's the angle phi. And that's also the angle phi. So that's a spatial rotation. And now let's verify that it is indeed a Lorentz transformation, that it satisfies this property up there. So that's where we have to calculate it a little bit. So I claim this is indeed a Lorentz transformation. So what do I have to show? I have to show that it leaves the eta invariant. So I have to show if I do something like this, I begin with the left-hand side. Eta mu nu, L mu rho, L nu sigma. And in order to evaluate this in a convenient way, I apply it to an arbitrary argument x rho, x sigma. And the goal is to show that this is eta rho sigma times x rho, x sigma for all x's. If I'm able to show this, then I have verified that it is a Lorentz transformation. So, okay, this here times this gives the x mu tilde. So this is x mu tilde, and this times this gives x nu tilde. And now I read the values of the tilde coordinates from this matrix equation. So this begins with eta naught naught, x naught tilde, x naught tilde. So this is just minus x naught tilde squared, right? Eta naught naught is 0. The mixed terms are 0. So I only have terms where these two indices are equal. The next one comes when both are 1. And then I have here a plus 1. And here I get x1 tilde squared. And equivalently for the other, x3 tilde squared. So that's it, what we have to calculate. And I can read this from this equation. So x naught tilde is the same as x naught. So this is minus x naught squared. Oops. x1 tilde is the same as x1. x2 tilde is cosine phi x2 plus sine phi x3. No, nonsense. Plus sine phi x3, and the whole thing is squared. This is this square here. And the last one, x3 tilde, is minus sine phi x2 plus cos phi x3. Minus sine phi x3 plus cos phi x3. Okay, and that can be easily calculated with the help of trigonometric identities. So x2 squared comes with a factor cosine squared plus sine squared, so that's 1. So I just get x2 squared, okay? x3 squared comes with a factor sine squared plus cos squared, that's again 1, plus x3 squared. And then there are two mixed terms. From this term I get 2 times cos times sine times x2, x3. And here I get minus 2 times sine times cos x2, x3. So the two terms cancel. And that's it. Okay? And now I rewrite this again with the help of my eta. This is eta mu nu x mu x nu, right? And this holds for all x's. And these things are symmetric, so the coefficients must be equal. So this must be equal to this. And that's what I wanted to prove. So this is indeed a Lorentz transformation. So spatial rotation is a Lorentz transformation. And obviously this is analogous for rotations about x2 and x3 axis. So for an arbitrary rotation about an arbitrary axis and an arbitrary angle, I need 3 parameters in order to characterize this. Maybe you remember this from mechanics. So for instance, you could use the famous 3 Euler angles for characterization of a rotation. So actually it's not a 1-parameter group. The 1-parameter group is only for a fixed axis. But actually it's a 3-parameter group. So you have this 3-parameter group of rotations included in the Lorentz group. So that's a subgroup of the Lorentz group. So that's a somewhat trivial example. More interesting example is the so-called boosts. About, again, I will do or about or along. Yeah, I think I can write about x1 axis. So that's something, so here the time played no role, right? The time coordinate was just kept fixed. So it was only about spatial orientation of axis. So now I bring the time into the game. A boost is something where really one inertial system is moving with respect to the other inertial system. And I want to consider the case that the motion is in the direction of the x1 axis. And because both are inertial systems, of course, the motion must be with a constant velocity. So the velocity will enter as a parameter. A convenient way is to use as a parameter not the velocity directly, but something which is given by the velocity. This is called the rapidity. I'm not sure if you have seen this before. So maybe you have not. But then I hope I convince you that this is a usual thing in order to parameterize boosts. It looks in the following way. So here I have a motion in the x1 direction. So in this case, nothing happens with respect to the x2 and x3 axis. So I have now here 1, 1, 0, 0, and also 0 in the mixed terms. And the interesting thing happens here. And here I have something which is similar to a rotation, but instead of cosine, which appears when I treat ordinary rotations, I have hyperbolic cosines and hyperbolic sines. So that's where some people call it a pseudo-rotation. I think there are, where's the minus sign? Both things. So I have here something like cos of eta, here minus sinh of eta, minus sinh of eta, and plus cos of eta. So the whole thing is parameterized by a parameter eta, and that's what we call the rapidity Some people call it a pseudo-angle because, well, it would be an ordinary angle if I had the ordinary cosine and sine here instead of the hyperbolic functions. So that's the reason why they call it a pseudo-angle. What does it do geometrically? Well, if I had the ordinary cosine and the other sine here, then I would get a rotation. So rotation is something like that, right? It rotates in this direction. And because I have here the hyperbolic cosines, it will go in this way. So one axis comes up and one comes down. So if you write this out and think a little bit about it, play around with the expression, you will find that it does the following. So if I have my original axis, here's x1, here's x naught. Now I, of course, plot this part of the coordinate system where I have where something interesting is going on, and we have to keep this part in our mind, which cannot be shown. And now I have my x naught tilde axis here and the x1 tilde axis here. Continue here. And here I have the same angle as I have here. And this angle alpha is determined by this rapidity eta. And what we have is that the tangent, that the hyperbolic tangent of eta is the ordinary tangent of alpha in the picture. So that's what you can verify if you play a little bit around with these expressions and plot this map explicitly. So here and we already know what the meaning of this angle alpha is. It has something to do with the relative velocity, right? So an observer which moves on this axis has the speed v over c equal to tangent alpha with respect to an observer which moves here. So I can write this as v over c if I want to express it in terms of the ordinary relative speed. So eta is just the measure for the relative speed. And now we can again verify that this is a Lorentz transformation. And then I will translate this into a notation which is probably more familiar to you, where we get the Lorentz boost in the traditional form. Boost, of course, I think the meaning is clear, right? Boost, I think in German it is anschieben. Yeah, also a booster is something which makes something which is at rest into something which is moving, and that's precisely what this transformation is doing, right? If I have something which is at rest in my original coordinate system, then it's moving with the speed v in the other system. So that's what is expressed by this word boost. And the motion is in the x1 direction, so that's why I call it a boost about or along the x1 axis. Okay, and because of this picture, some people call it a pseudo-rotation. So let me verify again that this is a Lorentz transformation. So we do exactly the same thing, and it's more or less the same calculation. Just instead of ordinary trigonometric identities, we have now to use hyperbolic trigonometric identities, right? That's the only difference. So I begin with the same expression, eta mu nu, L mu rho, L nu sigma, x rho, x sigma for arbitrary x. So this is eta eta mu nu, this times this gives x mu tilde, and this times this gives x nu tilde. And now I write this out. So this is, we know this now, it's x naught tilde squared plus x1 tilde squared plus x3 tilde squared. And shall I continue up there? So I read this now from this equation. So x naught tilde is cosh x naught minus sinh x1. And they have a minus sign in front of the whole thing. So a minus sign in front of the bracket, then cosh eta x naught minus sinh eta x1, and the whole thing squared. And then I have, one is missing here, okay. x2 squared plus x3 tilde squared. Should be 4 terms, yes. The second one, x1 tilde, is here. Minus sinh x naught plus cosh x1. oops, x1, and the other two remain unchanged. So this is x2 squared plus x3 squared. So you see, I get minus cos squared plus sinh squared times x naught squared, and this is minus 1, right? Cos squared minus sinh squared is plus 1. I have it here with the other sign, so I get a factor minus 1. The factor of x1 squared is plus sinh, minus sinh squared plus cos squared. That's plus 1. So I have plus x1, and the cross terms vanish. I get here the cross term with a plus, and here the cross term with a minus. So they drop out, and I only have these things here. And that's again eta rho sigma x rho x sigma. So this must be the same as this here, because it holds for all x's and it is symmetric. Yeah? So I have proven that this is a Lorentz transformation. And actually it is precisely the thing which I think every one of you knows as a boost. Let me just demonstrate this by translating it into standard notation. So what I need is this here. I need this here, that I have to identify the tangent of eta with v over c. So with a tangent of eta equal to v over c, we can express these expressions here, the sinh of eta and the cos of eta. Maybe some of you know it by heart. I do not know it by heart. So if the tangent, the hyperbolic tangent is v over c, then sinh is v over c over the square root. So this is v over c divided by 1 minus v squared over c squared. And I think the cos is just 1 over the square root. Yeah, this, if you have this, then these two equations follow just by standard identities for the hyperbolic functions. So I can insert this into the expression there, and then I can translate my formulas into standard notation. So x naught tilde is cos times x naught. That's 1 over the square root times x naught. And then I have minus sinh times x1 minus v over c times x1. And for the x1 tilde, I have minus sinh, that's minus v over c over the square root times x naught plus cos, that's just the square root times x1. Okay, now if we divide by c, then we get t tilde, it's t minus v over c squared, because I divide by c. And for x1 I may just write x. And then I have the standard textbook formula, which I think everyone has seen before, right? So that's the way in which the formula is given in most elementary textbooks. And here, if I just write x for x1, then I get here x naught is c times t, so this t drops out. I get minus v times t, and x1 is x divided by square root 1 minus over c squared. So this is the standard form of the Lorentz boost expressed in ordinary coordinates x and t. Y and z are kept fixed. So this is just slightly sophisticated way of writing the standard Lorentz boosts, and you see that you get a new geometric quantity. By this relation, it has something to do with the geometric appearance of this picture, and we will play around a little bit with this rapidity in the second worksheet, I think. I should also mention that, of course, in the limit c to infinity, you get the standard Galileo transformation, right? So I think I can squeeze this here. For c to infinity, we get the Galileo transformation. That's a transformation of for time and space coordinates in Newtonian physics. So t tilde is just t. If I send c to infinity, this drops out, and this becomes just 1. And here I have x tilde, this is 1. And here I have x minus vt. So that's the standard, well, that's the sort of transformation which we get from our naive understanding of space-time relations, right? So this is true according to special relativity only in the limit c to infinity. And this way we recover the Galileo transformation. I want to say anything more about this? No, I think that's, oh yes, I will. Since we have it on the board, I think I should briefly indicate that from these formulas you get the famous length contraction and time dilation. Yeah? I think everyone has seen this, but I should mention this because we have the formulas now on the board. Okay, so let me do this after cleaning the board. Okay, I should also mention, I have said that we have 3 rotations. Yeah, if you consider rotation about arbitrary axis, then we get a 3-parameter group. And about the boosts, of course, here I've considered only a boost in the x direction, in the x1 direction. Of course, I can also consider boosts in x2 and x3 directions. So you see the boosts are also characterized by 3 parameters. An important difference is that the combination of 2 spatial rotations is again a spatial rotation. But the combination of 2 boosts is not again a boost. Yeah, the combination of 2 boosts will in general involve a rotation. So in technical terms, this means that the boosts do not form a subgroup of the Lorentz group. But the common feature is that both things are characterized by 3 parameters. So I need 6 parameters altogether in order to characterize all possible combinations of boosts and spatial rotations, and that's actually the whole Lorentz group. So maybe I should write this down. So first of all, I should mention that you can consider boosts, of course, about an arbitrary axis. I've worked it out only for the x1 axis. And that if you do this, you get a set, not a group, but a set which is characterized by 3 parameters. So let me write analogous for boosts about x2 and x3 axis. How should I write this? Yeah, any Lorentz transformation. Well, actually, there's a slight restriction apart from discrete ones. What do I mean by this? Like reflections. I could just reflect one of the x's. I could rename x1 into minus x1. Yeah, I just reverse one of the x's. That would also be a Lorentz transformation. But that's something which cannot be continuously generated out of the identity with the help of continuous parameters. That's why it's called a discrete transformation. So if I leave out these discrete transformations like reflections, then the claim is true that any Lorentz transformation is a combination of boost and rotation. Is a combination and spatial rotations. But note that's a combination, that an arbitrary combination of two boosts is not a boost. So if I combine two boosts, first I consider a boost in this direction, so I change to another inertial system which is moving in this direction, and then I change to an inertial system which is moving with respect to the second one in this direction. Then the combination of these two transformations will involve a rotation of the axis. That's a famous Thomas rotation. It was found by a British gentleman by the name of Thomas. So it's called the Thomas rotation of the axis, which comes about if I combine two boosts. And that's the origin why spin axes seem to perform a funny sort of precession according to special relativity. This is then called the Thomas precession. So the background, the mathematical background for this Thomas precession is this fact that two boosts do not form a boost if they are combined. But nonetheless, if we just count parameters, so this was, so to speak, in brackets. So now this line of thought continues, and it says that hence an arbitrary Lorentz transformation is characterized by 6 parameters. That's what I mentioned last time already. So we say the Lorentz group is a 6-dimensional group. Yeah, I need 3 parameters for the rotation and 3 for the boosts. Okay, so much for this. And now we can quickly recall how we calculate time dilation and length contraction from the transformation of coordinate differences. I've written there the transformation for the coordinates. From this it's easy to calculate the transformation of coordinate differences under boosts. Let's quickly do this. There's a formula. Here, these formulas. So I now write this down for differences. So I get delta t tilde. Oops. Delta t tilde is delta t minus v over c squared delta x divided by the square root. And and delta x tilde is delta x minus, what was it, v times t, right? Yes. V delta t, v squared over c squared. So from these two formulas, we find immediately the formulas for time dilation and length construction. So let me quickly do this. By the way, the word is dilation. For some reason, it's just absolutely incomprehensible to me. Sometimes you find here in the dictionary TA, which is a linguistic nonsense. Yeah? It is differe de studi dilatum. So there's absolutely no reason to put another TA into this. So the word is dilation. So time dilation, what do we consider if we discuss time dilation? We have, I first draw a picture, then I explain it. So I have here x, here I have ct. And I consider two events which are at the same point in space with respect to my original inertial system. So in my original inertial system, where this is the world line of an object which is at rest, the two events take place at the same space with a certain time difference, delta t. So this would be my delta t, or rather c times delta t. And what's the time difference of these two events in another frame? So if I now change to another inertial frame. So here I have ct tilde. Then I have an x tilde axis here. And I project now parallel to this spatial axis. I project in this way. And then this here, this time difference, now red from the t tilde coordinate, which goes along this axis. That's my c times delta t tilde. And I want to know how are these two things related. And as this is called time dilation, obviously we expect that this will be longer than delta t tilde will be longer than delta t. And we can just read it from this formula because the two events take place at the same point in space with respect to the original coordinate system. We have delta x equals 0, right? So delta x would be the difference in the x coordinates for these two events, but this is 0 by assumption. So I just read from this formula how delta t tilde and delta t are related. So this gives us the famous formula for time dilation, delta t over the square root. So that's it. So obviously because, this thing here is smaller than 1. Yeah, I subtract something from 1. Because it's in the denominator, the factor with which delta t is multiplied is bigger than 1. So I have a dilation, it becomes bigger. So that's time dilation. I think I don't have to discuss this, everybody has heard about this. And then we do length contraction, also called Lorentz contraction, because actually Lorentz derived this formula before Einstein, but he interpreted it in the wrong way. He thought that really a material body would be deformed in the way that the matter would be compressed together by this effect. But it's just a transformation effect of coordinates. Yeah? I view the same thing in terms of other coordinates. So it has nothing to do with really a physical compression of the body. So the interpretation of Lorentz was completely wrong, but the formula, actually, which he wrote down, this is perfectly correct. This is perfectly right. So in this case, I consider the following situation. I have a rod or something like that. So the left-hand side of the rod has this word line. The right-hand side of the rod has this word line. And then this here, so this here is a rod. Write it in this way. And this distance here, this is delta x. Yeah? And I want to know what is the length of the rod in a moving system. So if I now introduce another inertial system, ct tilde has another spatial axis x tilde. What's the length with respect to this? So what I have to do is, I have to, how do I draw this? Okay, I'll say something about this later. So what the length of the rod in the moving system is of course defined in the way that I have to consider two events which are simultaneous in the moving system. Then I have to see what is the spatial distance of these two things. So it's the left-hand side of the rod is if an event A takes place at the left-hand side of the board, then the event which takes place at the same time in the twiddle system at the other end of the rod is this event here. So that's the difference which I have to consider. So that would be my delta x tilde. And in this case, the delta t is 0. Yeah, because the events, the delta t tilde is 0, right? Yes, in this case, delta t 0, delta t tilde is 0. Yeah, the two events A, B take place at the same time in the twiddle system. So that's the formula I have to use. So what do I want to do now? I want to get something about the axis. The T. Oh yes, of course. Here's the formula. That's the formula I need. So I have delta t is v over c squared delta x. And this gives me a relation between delta x tilde and delta x. So I have delta x tilde is delta x. This is, no, I eliminate the delta t. So I write delta x and minus v times delta t. V times delta t is v squared c squared delta x. Now I get it. Square root 1 minus v squared over c squared. And you see I can divide by the square root, and then I get the formula which I wanted to get. No, the square root is now in the numerator. And that's a contraction because the factor is smaller than 1, right? It's now in the numerator. So this factor is smaller than 1. This means the delta x, which is the length in the rest system, is now made smaller. It is contracted. Wait a minute, look at the picture. Delta x tilde is smaller than delta x? Looks different in the picture, right? Did I make a mistake? What do you think? Should we trust the formula and say, okay, delta x tilde is smaller than delta x? Or should we trust our geometric intuition, looking at the picture and saying delta x tilde is bigger than delta x? What is correct? I claim that both is correct. The picture is correct and the formula is correct. What could be, yeah?
Change the scaling.
Exactly, exactly. So if you say this is bigger than this here, what you implicitly do is you assume that the length unit on this axis is the same as the length unit on this axis. This means that you just take a compass and throw a circle, and then you get the unit here and the unit here. But that's not the case. The scale on this axis is different. And actually we will do this on the second worksheet. You will see that the scale on this axis is bigger. And that's the reason why this length, really measured in the twiddled system, is actually smaller than this length. So you should be careful with wordline diagrams. I like wordline diagrams. You have already realized this. They're very helpful, but sometimes they are a bit deceptive. So you have to be a little bit careful. You should not overemphasize them. You should not overemphasize the things which you can read from the pictures. Okay, so much for Lorentz transformations. We will come back to Lorentz transformations later. So in particular, we will see that Maxwell's equations are Lorentz invariant. And we will talk also a little bit about Lorentz invariance of certain matter equations. We will talk about the energy momentum tenses for matter. And then again, we will come back to Lorentz transformations. But for the time being, we leave them now. But what we should keep in mind is that this postulate P1, which included the statement that all inertial systems have equal rights, that this implies that laws of nature must be invariant under Lorentz transformations, right? Because Lorentz transformations take inertial systems into inertial systems. So that's something to which we will come back later, frequently. But what I want to do now, before we come to Maxwell's equation, I will talk a little bit about particles, motion of particles, as both kinematics and dynamics of particles. And by particle, one usually means a massive particle, so something which moves with a speed smaller than the speed of light. And in the following section, we will then also talk about particles which move at the speed of light. So that's what you could call a classical photon. And well, what we discuss in these sections, this will become quite relevant later when we move to general relativity, because light rays and freely falling particles will be the most important experimental tools for measuring gravitational fields and checking the predictions of general relativity. So particles and photons, classical photons, will accompany us through the whole course. Okay, so that's section number what? 2-4? I think so. Yes, 2-4. Kinematics and dynamics of particles. So when it says particle, without any any specification, then one usually means an object which moves at subluminal velocity. So one excludes the case that it is a photon. So we require that particles move at subluminal speed. And what does it mean? Well, it means that the world line of this particle must satisfy a certain inequality. The world line. The world line would be something like x mu. That's the 4 coordinates of the particle. And this would depend on a parameter, which parameterizes the world line. I call this parameter tau. And I will talk about how to choose this parameter in a minute. So the world line must satisfy a certain condition. Well, in terms of a picture, we can immediately say what the condition is. So if I have here my space-time in a certain coordinate system, x0, which is ct, and now my world line of the particle is something like that. And the condition that it moves at subluminal speed means, if you remember, that the tangent vector must be inside the light cone, right? So at each point I can draw the light cone, and the condition is that the tangent vector to the curve must be inside the light cone. So it must be what we call the time-like vector. Yeah? Remember, time-like were the vectors which lie inside the light cone, light-like were the ones on the boundary, and space-like were the ones which point in the to the outside. So geometrically the condition is that the tangent vector, well, the tangent vector can be written in this way, of course, dx mu by d tau, that this vector must lie inside the light cone. And this can be written with the help of our Minkowski metric, dx mu. So what's the condition this expression has to satisfy? Remember, well, if it would lie on the light cone, what would this be, this expression? If it would be on the boundary. Well, it would be what? Remember? Not yet familiar with this object, I see. So we have to practice it. Remember the equation of the light cone? It was I used it when I proved that these two things which we discussed were Lorentz transformations. I had exactly this expression on the board. So for light signals, well, write it out if you don't remember it by heart. So we have minus the x0 component squared plus the 3 spatial component squared. What should this be if we are on the boundary? Where the spatial length, the difference of the coordinates of this point and this point, the spatial length difference must be the same as the temporal length difference if I put the factor c in the right place. So this eta must be, if it is on the light cone, it must be 0. Remember? Yeah. If it's on the light cone, then it is, oh, we have to repeat this. Yeah, if this is not, this is really important. And now with my sign conventions, I had defined it in a way that the temporal component comes with a minus sign. With my sign convention, the time-like vectors have negative values for this expression. So that's the condition. Yeah? And the space-like vector, which point to the outside, they have a positive sign here. I told you that other authors use the other convention. Then they have all equalities just the other way around. Yeah, you have to be careful when you compare with the literature. Okay, we have to repeat this. I see. Where shall I do this? So I had defined yeah, let me do it here. When we did this, I considered differences of coordinates. And I said that the difference vector delta x mu is time-like, light-like, or space-like if the following expression, if minus delta x naught squared plus delta x1 squared plus delta x2 squared plus delta x3 squared is, no, not equal, is minus smaller than 0, equal to 0, or bigger than 0. And this has an obvious geometric meaning. This is the length difference squared. Yeah, you see Pythagoras. Yeah, that's the length difference squared. And this is up to the factor c squared, it's a temporal difference squared. And if these two things are equal, this means if I write this on the other side, I get a 0. Then this means that I have an inclination of 45 degrees. Yeah? So it's a claim that this here is the same as this here. So then I have here 45 degrees. If this delta c times delta t is the same as this delta x, which is the square root of this thing. Yeah? So if I want to have 45 degrees here, then I must have the 0. If I want to have something which is, well, I usually talked about this angle here, which is, of course, in this case the same. That's what I called alpha. Yeah? So if this angle is smaller than 45 degrees, then this term is bigger than this here. Yeah, it gives a bigger contribution than this here. So then I have this equality sign. This means then I'm inside the light cone. So then I have a time-like vector. And if I am here, then I have something where this equality sign is true, and then it's bigger than 0. So I think that should be really easily understandable, yeah, if I write it in this form. And what I've done now is I've just rewritten this expression with the help of this funny eta symbol. Yeah? If I do this, then this here becomes just eta mu nu delta x mu delta x nu. And that's easily verified. You start with this expression. Remember what the etas were. Yeah, eta naught naught is minus 1, eta 1 1 is plus 1, eta 2 2 is plus 1, eta 3 3 is plus 1, and all the mixed terms vanish. So you get minus delta x naught squared, here it is. And then you get plus delta x1 squared, here it is, plus delta x2 squared, and plus delta x3 squared, and no mixed terms. Yeah, it's just a comprehensive way of writing this expression with the summation convention. Yeah, summation over mu, always understood, mu and nu. So from this consideration, which I actually hoped that it has arrived in your brain, with this consideration we find immediately that a particle must satisfy this condition. Yeah? So that's a tangent vector. That's a tangent vector must point to the interior of the light cone, so it must satisfy this inequality. And well, here I take a derivative with respect to a parameter tau, and now we may ask, how do I choose this parameter? Is this completely arbitrary? Well, first thing you should realize that is choosing the parameter has nothing to do with changing the motion. Yeah? If you choose one parameterization for this curve and I choose a different parameterization, this doesn't mean that we consider different motions of the body. The motion of the body is given just by the shape of this curve, because the time coordinate is here. Yeah? So the world line, without any parameterization, already tells you when and where the particle is at a particular instant. Yeah? So the parameterization has a different meaning. It has nothing to do with really influencing the motion of the thing. What does a parameter do? How could you interpret the parameter? Have you an idea what physical interpretation could be given to a parameter on this curve? With which physical apparatus would you associate such a parameterization? It assigns numbers to each event on the world line. So to each event where this thing is present, it assigns a number in a continuously increasing way. How would you call such an object? Who says, well, if this is my word line, it says, now here at this moment, this is 1, and at the later moment, again, where I am, this is 2, then it is 3, then it is 4. Well, I'm carrying such an object with me, which does this assignment. It's here on my wrist. That's the thing which does this. It assigns numbers to each event where I'm present. Yeah? That's what we call a clock. So the parameter is can just be interpreted as the reading of a clock. So the question is, what clock should we give to a particle? Is there a distinguished choice of clocks? You could choose anything. Yeah? Any clock would parameterize a word line. But is there a distinguished choice? Well, let's discuss this question now. And actually, there is a distinguished choice. And I will discuss this in 2 different ways. First, from a formal point of view, just looking at the equations and then saying, well, maybe we can find just from a formal idea a particular parameterization. And then we will discuss what it physically means. Is there a distinguished choice? For the parameter. Well, just look at the dimension of this thing. So the etas are numbers. Yeah, they're just numbers, +1 or -1. And this is, all my x's have the dimension of a space. Also the x naught has of a length, has a dimension of a length because it's multiplied with a c here. Yeah? So this is length, and of course my tau should have the dimension of a time. Yeah, if I want to interpret it as a reading of a clock, it should have the dimension of a time. So I have length divided by time. So I have a velocity, the dimension of a velocity. So that's something which is a velocity squared. And now in special relativity, is there a distinguished velocity? So is there a distinguished value which we could give to this negative thing? I think from a formal point of view, a very natural choice is to normalize this to -c². Yeah? Minus because it should be negative. And, well, something with the dimension of a velocity squared, the natural choice for this would be the velocity of light squared. Yeah? So my claim is, yes, choose tau such that this expression, which could take any values, yeah, if you reparameterize the curve, then the tangent vector becomes longer or shorter. So you could get any negative value to this quantity just by reparameterizing. So do it in such a way that the thing is normalized to -c². dx mu tau is -c². So if people choose a different signature where they have 1 plus sign and 3 minus signs, then they have a plus here. Yeah? Don't be confused if you find a plus sign in some books. It was right there. So that was a purely formal idea. Yeah? Just because a theory distinguishes a particular velocity, then let's choose this expression here. But is there a physical idea behind this? And what I claim is that I can interpret this in a particular way, namely if I compare it with a time coordinate in an inertial system where this particle is at rest. Of course, this can be done only for particular events, yeah, because the particle moves in an accelerated way. Here at this moment, it is at rest in the inertial system which I have chosen. Yeah, here the tangent is vertical. But here at this moment, it is at rest in another inertial system, where this is the x naught axis. So I can do this for any event on the word line, and for any event I will get a different system. So that's what I call the momentary rest system. I can do it for any moment. In the momentary rest system, this means I consider a moment where my spatial coordinates, yeah, Latin indices only takes the values 1, 2, 3. And I do this in such a way that this is 0. Yeah? So this can hold in a fixed inertial system, usually only at one particular event. At another event, it will no longer hold. So that's the reason why I put the 0 here. It's a particular value of the parameter. So here, for instance, at this parameter value tau naught, tau runs along this curve. That's where I have tau naught, and then the tangent is precisely vertical. So in this event, this equation holds. Tau is related to t in a particular way, and that's what we want to calculate now. And this gives us the right idea how to interpret this particular time coordinate tau in a particular way. So we calculate this now. Oops.
Question?
Yeah?
Don't we have to insert the tau 0 after taking the...
Yes, that's what I mean. That's what I mean, yeah. Okay, yeah, the notation is a little bit dangerous. So what I mean is I take the derivative with respect to tau, and then I insert the value tau naught for the tau. Okay, some people write it in this way. Yeah, you prefer this? But what I meant was this. Yeah, it's just somewhat shorter notation. Okay, what do I want to? Yes. Oops. So what I have to evaluate is now this equation here. This equation here, I have minus c squared. That was a general definition. dx mu by dx nu. No, sorry, by d tau, of course. Dx nu by d tau at tau naught. And now I am in the rest system, in the momentary rest system. So the only terms which give a contribution are the ones where the index mu and nu takes the value 0, because the other terms go away. So I only have the first term, the eta naught naught dx naught d tau squared at tau naught. And this, of course, is minus 1. And x naught is c times t. So this is c squared, if I take the square into account. And then I have dt by d tau squared at tau naught. So if I divide both sides by minus c squared, I see that dt, well, both things proceed in the same direction. So I have to take the positive square root, right? If tau is increasing, t is also increasing. So I have the positive square root. So I have dt by d tau at tau naught is 1. What does this mean geometrically? It means that, well, as I said already in the picture, it means that the tangent vector is vertical. Yeah? And this means that the increment of the t coordinate is momentarily, at this instant, the same as the increment of my parameter. So for a very short time interval, which approximates the world line by its tangent line, for a very short time interval, I can identify t with tau in this inertial system. So tau is a time which is associated with an inertial system in which the particle is momentarily at rest. Yeah? But if the particle is always at rest, if it's just a straight line, then t would be the same as tau. But if it moves in an accelerated way, then I have to do it for every event individually. So it's a reading of the coordinate of a coordinate clock in a system where the particle is at rest. And so if we are in the system in which the particle is at rest, that's the system which is in a natural way associated with the particle. And that's why we call this time proper time, or in German, Eigenzeit. Yeah? So that's a formal definition. And that's the interpretation, which tells us what it means in terms of a distinguished inertial system. So tau is a time which is indicated by the coordinate time in the system in which the particle is at rest momentarily. Oops. So proper time is a very important concept. So at the moment we are talking about proper time in special relativity. We will then generalize it into general relativity, where it will be given by a very similar equation like this. We just have to modify the eta a little bit. So the eta will be replaced by something more general. But apart from this, it will be exactly the same equation. So if somebody asks you what is proper time, then you should write down an equation of this form. Yeah, that's what proper time defines. So for this reason, or let me write first. So for sufficiently short time intervals, and sufficiently small means the time interval should be so small that I can replace the world line by its tangent. Yeah? So for a very short time, the world line is more or less straight. I cannot distinguish it from a straight line. And that's a condition which must be satisfied that this approximation can be done. So for sufficiently short time intervals, delta tau is a valid approximation. Oops. For delta t in the rest system. And for this reason, because the rest system is a system which is associated with a particle in a natural way, which is its proper system in a certain way. So tau is called proper time. And a clock that shows proper time is called a standard clock. Question is, of course, whether standard clocks exist in nature. Is it possible to give a standard clock to each particle? Well, according to our experimental experience, this is possible, and the atomic clocks, which we are using, actually turn out to be standard clocks, to within the accuracy of any experiment which is known until now. So that's something which has to be tested by experiment. Actually, it's not absolutely true clear that this is true for arbitrarily strong accelerations. One could expect that if I have an atomic clock and I accelerate it very strongly, that it will no longer be a standard clock. But this point has not been reached until now by experiments. So up to now, or to date, all experiments indicate that atomic clocks are standard clocks. So atomic clock is an experimental notion. Yeah? Atomic clocks are the things which are standing at the PTB in Braunschweig, these big cupboard-shaped clocks which give the time signals which you receive over TV or whatever when you set your clock. And standard clock is a theoretical concept. Standard clocks are defined theoretically by an equation. Yeah? And the question is, are the two things the same, or to what accuracy are they the same? And until now, apparently, there's no reason to assume that they are not the same. So when we interpret experiments on the basis of special or general relativity, all these experiments involve the time in some way or other. Maybe frequencies are involved. Frequencies are inverse times, right? So practically every experiment involves a sort of time. And what we do is that we identify the time which is really read from atomic clocks in the experiment, that we identify with this with the theoretical concept of a standard clock. And the experience is that this works until now. So when sometimes there's a contradiction between experiment and prediction from relativity. It could be in this identification. Yeah, it could be that that's the reason, that we have reached the point where actually atomic clocks do no longer behave as standard clocks. Okay. Actually, there are alternative theories, alternative to Einstein's theory of relativity, in which this is no longer true, where atomic clocks are no longer standard clocks. Actually, I wrote my PhD thesis about one of these theories, the theory which was brought forward many, many years ago by Hermann Weyl, by the mathematician, which I mentioned last time. So this Weylian gravity, which is an alternative to general relativity, is a theory where this identification cannot be made. But until now, there's no reason that Weyl's theory is a correct one and Einstein's theory is false, just the other way around. Okay, that's the definition of standard clocks, and in particular of proper time. So we have now a particular parameter for each world line. So we can now normalize or we actually already have normalized by this condition our tangent vector. And this normalized tangent vector is called, as probably everybody knows, is called the 4 velocity. So we associate a 4 velocity with every particle. And if we differentiate this another time, you get the 4 acceleration. And we'll now talk a little bit about these two notions. These two notions make sense only after you have fixed the parametrization. Yeah? As long as you leave the parametrization open, the 4 velocity is only defined up to an arbitrary factor, which may vary along the curve. And the 4 acceleration is not defined at all, because it can take virtually any value. But I will never use parameters other than proper time when we speak about particles. You already see that this notion of proper time doesn't make sense for particles that move at the speed of light. Because if the particle moves at the speed of light, so if it is what we call a classical photon, then we would have equality here. And then, of course, you cannot normalize the thing. Yeah? If it's 0, you cannot normalize it. So photons have no proper time. There's no notion of proper time for photons. That can already be seen here. Okay, we define now the 4 velocity. So that's usually denoted u mu. It depends, of course, on tau, and it is just this derivative. And because of our normalization, this satisfies eta mu nu u mu u nu minus c squared. This could happen frequently, because as I already mentioned, when I do calculations for myself, I always set c equal to 1, and then of course I have here minus 1. So I try not to forget this, that we have not set c equal to 1. And the 4 acceleration is the whole thing differentiated another time. That's usually denoted a mu. So this is the derivative of u mu by tau. It means that it's the second derivative, x mu by tau squared. So, of course, you are familiar with the notion of a velocity, but I think most of you will think of a velocity as a 3 vector. Yeah, just velocity with respect to the curve in space. So dxi by dt, that's what you would usually call the components of the velocity in what you are familiar with from non-relativistic physics. The question is, what has this 4 velocity to do with this ordinary notion of 3 velocity? The relation is not quite trivial. You might think that it's just the first 3 coordinates of this thing, but that's not true. And that's the reason why I want to emphasize this. So let's calculate this. How is u mu related to the ordinary, or what you might call the 3 velocity, 3. So this would be defined as dxi by dt, not by tau. Yeah, you would do it with respect to the coordinate time in which you are sitting. So that's what you would call the ordinary 3 velocity. So let's denote this vi. Well, I have to do a little calculation in order to find this out. How do I begin? Let me check. Yeah, first I should mention that, well, if we give our x, or our x naught, x1, x2, x3, x function of tau, and you want to calculate this, then we would of course do it with the chain rule. So we would write this in this form. So the question boils down to the question, what is dt by dtau, or dtau by dt? Yeah? Tau is proper time, which runs along my particle, which is defined by the equation which I have put on the other board. And t is a coordinate time in the inertial system in which I'm sitting. So that's what you can read from the axis. And the question is, how are these two things related to each other? Well, as we have just talked about time dilation, you will already guess how they are related. You will get this famous square root factor, of course. But let me derive this in full. So that's the question we want to deal with. And I think I write just down the defining equation for proper time. Yes, and then I juggle around a little bit. So the equation which I have is this here. So this was eta mu nu dx mu d tau dx nu d tau, right? So I can decompose this into temporal and spatial components. So I had the naught component. This gives a minus sign here. And then dx naught by d tau squared. And the other three come with a plus 1. So I get plus dx1 d tau squared plus dx2 d tau squared plus dx3 d tau squared. Okay, the first thing, x naught is c times dt. So this is minus c squared and then dt over d tau squared. That's the expression which I want to determine, right? That's why I do the calculation. I want to find out what this is. And what I get here is, well, it's not dxi by dt. This would be my v. It's dxi by d tau. So I can write it in terms of the v if I multiply by this expression. Okay, let me write it slowly. So this would be my v1. That's dx1 by dt. And then dt by d tau. And the whole thing squared. Plus my v2. dt by d tau. And the whole thing squared. Anything wrong? Anything wrong? Okay, now you see I can take a dt by d tau out of the bracket. And what do I get then? I get minus c squared. Yeah, could be. Minus c squared, v1 squared plus v2 squared plus v3 squared. Okay. So I get minus c squared I had on the other side. And here I have dt by d tau. Minus c squared. Well, and for this, I write just v squared. Yeah? It's the magnitude of the velocity squared. So I write just v squared for this here. So if I divide by minus c squared and take this to the other side, I get dt by d tau is, oh well, I can't do it in one step. Let's do it slowly. Then I have minus divided by minus, That's 1 minus v squared over c squared, right? And now both t and tau are increasing in the future direction. So if I take the square root, I have to take the positive one. So I get dt by d tau is plus 1 over root 1 minus v squared c squared. And I think you recognize now the time dilation formula in an infinitesimal version, right? It's only for a small interval where I can approximate my, my curve. Well, we had deltas before, and this replacement, to replace the d by delta, is allowed only if my world line is a straight line, which is the case which we had considered before, right? So for arbitrarily short portions of the world line where the deltas can be replaced by deltas, the d's can be replaced by deltas, we get the time dilation formula. So for this, we now get the relation between the 4 velocity u and the 3 velocity v. So this was a general formula. So we have now vi is ui, that's ui, right? U was defined as a derivative with respect to tau times d tau by dt, and d tau by dt is the square root of 1 minus v squared c squared. So you see the spatial components of the 4 velocity are not the 3 velocity. And that's the reason why we use different symbols. Yeah? If you use a symbol v for both things, then you run into trouble. Yeah, this won't work. It would confuse things. That's the reason why we should distinguish them. And the usual convention is to write u for the 4 velocity and v for the 3 velocity. Okay, should I stop here? So the next thing I want to do is to discuss uniformly accelerated motion, and I think we do this next time. I don't have time today to do this. So I think we stop a little bit early today. Have questions? I was a little bit worried when nobody was able to to get this inequality to here. So are you completely unfamiliar with this eta? Is this really something which looks strange to you, where you don't have the feeling that in a reasonable amount of time you can get familiar with? I think we do a little bit of exercises with the eta on the second worksheet, but we don't have time to spend weeks on this, of course. We have to proceed to general relativity fairly soon. So actually I thought this was just a recap of things you knew already, maybe in a slightly different language than you were used to, but not the subject itself should be new to you. So do you feel already lost? No, okay, good. So I hope when we have done the second worksheet, maybe then we will feel a little bit more comfortable. Oh, I should tell you the next tutorial, of course, will be this Wednesday. And this Wednesday we have in our Graduiertenkolleg the first colloquium. So I will be away on Wednesday, and also some of you will be in Bielefeld, right, where we have this colloquium. But I think that's no reason to cancel the tutorial. I think you can do it without me. Yeah, what I will do is just I will send the sample solution to one of you. Dennis already volunteered to do this. So I will send the sample solutions to him. So he will have the solution. And then hopefully one of you will come to the board, try doing the exercise. And if you get stuck completely, then you will have the sample solutions and can do it hopefully with this. So I think this should work. I guess you are old enough to do it without me. So next Wednesday I will not be around. But of course, you have always a chance to ask me questions by email. I usually answer my emails fairly quickly. Not always, but usually. So we will have the next lecture then on next Thursday. Okay? Okay. Have a nice weekend.